Hey, welcome back to Mabuhay Mathematics, everybody. This is part 2 of common mistakes taught in maths class, I can say particularly in the US. In a moment, we'll pick up right where we left off in the first video, so if you haven't seen part 1, you might check that one out first, then circle back to this video. Before we get going, here's a quick review. The issues we're addressing are the definition of absolute value, the square root of x squared for real values of x, and the phrasing, the function f of x. In part 1, we clarified that if we want to define distance using absolute value, we shouldn't define absolute value using distance. And since we want to do some algebra anyway, we covered the algebraic definition of absolute value, which is split into cases depending on the sign of what's inside. We also said that we can represent this in piecewise form so that the result is clear based on the sign of x. Which brings us to mistake number 2, that the square root of x squared always equals x. Let's do some math. Let's start right away with an example that illustrates the problem. Consider x equals -5. The square root of x squared becomes the square root of quantity -5 squared, which is the square root of 25. The square root of 25 is 5, but x was -5. So the square root of x squared didn't reduce to x. So, although the magnitude of these expressions was the same, they have different signs. Even though x was negative, the square root of x squared was positive. But wait, I thought the square root of 25 was plus or minus 5, not just 5. What's the deal? Again, we need to clarify our terminology and notation so that we're on the same page. So let's actually define the square root of x squared. Let x be any real number, then I think we can agree that x squared is non-negative. But let me know if you have any doubts about that in the comments. We define the principal square root of x squared, which we denote using the usual root or radical sign as the absolute value of x. If this is the first time you've seen the square root of x squared reduced to the absolute value of x, go ahead and say it out loud with me. The square root of x squared is the absolute value of x. The square root of x squared is the absolute value of x. And this is true for all real numbers x. So that means that when we use the square root symbol, it implies automatically that we're referring to the principal square root, which can't be negative. It's in an absolute value. So when we write the square root of 25 like this, it reduces to 5, not plus or minus 5. Let's see how this might be valuable to us in an algebra class with an example. Say we want to solve x squared equals 25 for x. Recall from part 1 that if c is greater than or equal to 0, the absolute value of x equals c. That equation can be rewritten as x equals plus or minus c. Hint, this is actually where the plus minus comes from if you've seen that show up in an algebra problem after a square root. So, from x squared equals 25, we can take the square root of both sides. And at this point, I won't keep saying principal every time because we virtually only ever mean the principal square root, at least when we're this far along in our math class. So we replace square root of x squared with, what was it again? Great thinking, the absolute value of x. On the other side, we take the square root of 25, which is 5. Using the absolute value rule that you can see on the slide, we remove the absolute value bars from the x and allow the value on the right side to be either positive or negative, and in this case we've isolated x. So this is the solution. X equals plus or minus 5. So now we have a better sense of absolute values and square roots, and we've even found out that the two are related. Absolute values are built into the definition of square roots, and so our knowledge of absolute value became directly relevant in the square root problem. It turns out both of these topics are also related to our third common mistake, that the creature we call f of x is a function. In algebra class, it can be easy to get away with a sense of functions that's limited only to formulas like a formula for y given x, and graphs. While both of these perspectives are certainly important, to resolve the issue at the top of the slide, we need to clarify our, can you guess what? Two things, terminology and notation. So to get a better sense of what a function is and does, we can think about anything made by a machine or even a factory. But on the right side of the slide, we just saw a 3D printer printing out an object. Looks like a skull. Ooh, spooky. So why do we want to think about objects made by machines? because conceptually, that's how a function works. So in our 3D printer example, there's some input coming in. What you see here are spools of filament, basically the material that's used to create an object with a 3D printer. There's the machine, in this case the 3D printer, and that takes the input and does something to it. And out of the machine comes some object. So for the 3D printer, the input is the filament, the machine is the 3D printer itself, and the output is the 3D printed object. I didn't want to scare everyone with the skull every time, so I use a picture of these 3D printed orange doodads. Let me know in the comments if you have any idea, or maybe you know what purpose these little doodads might serve. Back to functions, there's an analogy that we want to make. Every function has some type of argument that acts as an input. There's the function itself, which is the machine that takes the input and turns it into something else, and the thing that the function churns out, which is called the value of the function. Some common symbols we see taking these roles are x for the argument, f for the function, and f of x for the value, specifically the value of the function f with argument x. When we want to refer to the function itself, rather than saying f of x, which is the value that comes out of the function, the 3D printed object, we should say the function f. Let's look at these same terms and symbols in the context of an equation that shows up all the time, y equals f of x. Again, x is the argument or input of the function, f is the function itself, or the machine that's taking x and transforming it into something. And now y and f of x are equivalent representations of the value of the function f at x. We typically use y when we want to emphasize its identity as a variable, specifically the dependent variable to x's independent variable. And we use f of x when we want to emphasize that it's the value of a function. Outside of machines, we can use this framework for other input-output relationships. If, for instance, you're paid per hour or per year, there's a function that takes in time that you worked as an argument and puts out your earned income as the value. If you're a climatologist, if you're a climate scientist, you might think of the average temperature across the Earth or in some region of the Earth as the value of a function with arguments like greenhouse gas concentration, solar radiation, vegetation cover, how green is it around the Earth, and probably several others. All right, all that was pretty abstract, but you're hanging with it. That's awesome. Let's simplify things a bit and understand on a very concrete level why it's not correct to call f of x a function for the functions we typically come across in algebra. Keep in mind, f is the function, f is the machine here. So x, the argument of the function, is a number. Y, the value of the function, also a number. If y is a number and y equals f of x, then f of x is also a number. And so, just like the orange doodads that come out of the 3D printer are literally different objects than the 3D printer itself, f of x, a number, is a different mathematical creature than f, the function that produced that number. This mistake, by the way, you can find it all over the place, including in textbooks that are used at least all over the US. So you can cut your teachers some slack if they make this mistake, but I also challenge you to rise above it and to use these terms and symbols correctly whenever you're doing maths or talking about maths. As a quick extension, to emphasize that functions are different creatures from the numbers they produce, let's look at some of the ways we can combine existing functions to create new ones. Here, f and g are functions, and for all of the following equations, we're going to ignore any domain restrictions, just to simplify things, and just assume x takes a valid quantity so that everything we see is defined. On the left, we have 4 new functions defined from f and g, the sum, difference, product, and quotient functions. For instance, to evaluate the product function f times g at x, we compute f of x and g of x, then take the product, f of x times g of x. On the other side, we have some function compositions. G composed with f is a new function, and to find its value at x, we take the value of f at x and use that as the argument for function g. The value of f becomes the argument of g. These types of functions have several important applications, If we take the composition of inverse functions on the proper domain, the value of the composition is just x. That's what we're seeing in equations 2 and 3 on the right side. The value coincides with the argument. This actually says that composing two inverse functions together forms a special function that we call the identity function. The identity function, we can call it I, is just the function that spits out the argument as its value. So ignoring any domain issues, f composed with f inverse is going to be the same function as f inverse composed with f, both of which just represent the identity function I, where I of x equals x. The value of I equals the argument. Wasn't that fun? One more thing I'll throw out there. Even deep learning and artificial intelligence relies heavily on function composition. So having a handle on functions at the fundamental level can actually benefit you in the realm of machine learning too. I know we're at algebra right now, but this is just one of the ways that this stuff is actually used out there in the real world. Let's recap what we learned across both of these videos. Here are the 3 mistakes we addressed. First, we showed that defining absolute value using distance can lead to a circular definition and instead introduced the algebraic definition of absolute value. That absolute value equals x when x isn't negative and equals negative x when x is negative, thereby producing a positive value. Next, we clarified that we can't say the square root of x squared equals x for all real values of x, though it is true for x greater than or equal to 0. What about when x is negative? That's why we define the square root of x squared as the absolute value of x. It covers both cases. This definition also happens to connect square roots to absolute values. Finally, we addressed the phrasing in the function f of x. We established that f of x represents the value of the function f at x, which is actually a number. And so when we refer to the function, we should say the function f. Wow, you all. Great work. By the way, the connections between these topics don't stop at absolute value and square root. I mentioned it a little earlier. It turns out both of these are also related to functions. That's a conversation for another video, but if you think you know what the connection is, go ahead and share your thoughts in the comments. Thanks for watching, everyone. If you've ever encountered any of these mistakes before, go ahead and like the video. You can subscribe to our channel for more mathematics content. Check out our tutoring services at mabuhay-maths.com. Let us know in the comments if you have any other questions. Drive under the speed limit, not under the influence. Take care of yourselves. Take care of each other. I'll catch you next time.